My name is Roshan John, and I'm the team leader for Team Cryoneers, participating in the Space Science Challenge 2021. Our project is called Project R2S2, that stands for Reused Rocket Stage 2. Being in the rocketry part of the competition, our focus is in the launcher industry, and especially since a lot of small sat launchers are getting the spotlight now. Recoverability is a hot topic right now, but it generally applies only to the first stage, as the upper stages are harder to recover due to the high delta V. Our solution is to reuse the second stage rather than recover it, by attaching instruments and sensors, converting the stage into a satellite, with station keeping and orbital maneuver capabilities. Our approach to the solution is to demonstrate it with a real-life mission. The mission chosen in this case was Flight VV-17 by Arianespace, the 17th to be performed by the Vega launcher. The primary payloads are two satellites, both to be deployed at sun-synchronous orbits. The launch was scheduled to be on November 16th, but failed.
Hi, I'm Brunmay. Starting off with the feasibility study, our solution is particularly based on two feasibilities, physical feasibility and a logistic feasibility. We are using CAD modeling for the physical feasibility approach to make sure that we can place additional sensors. Logistic feasibility is considered to study other mission aspects and also the cost comparison. The approach solution is studied by considering one example mission and also by learning how the above two feasibilities can be achieved using this solution. For evaluating the feasibility, a specific research topic is considered to be studied using R2S2 approach. Our mission is to study the field aligned currents from the magnetic fields as well as by the observations. And for this, the required additional payloads would be digital flux gate magnetometer and one camera. These FACs are associated with aurora, and these can be calculated using magnetic field perturbations. Earlier study used a magnetometer as well as satellite constellations for these calculations. Our R2S2 approach would verify this research using a small size magnetometer for magnetic field calculations as well as for the attitude determination. And we are also going to use camera that would collect all observable auroral images.
Hi, I'm Federico, and I will explain the physical feasibility in the next slides. The physical feasibility was determined by studying if it was physically possible to incorporate additional sensor into the module, and if so, in a feasible way. In order to do that, the Vega user manual was used to be able to determine the space available to fit sensors, solar panels, and respective supports into the conical adapter. Once the position of the supports and sensor was decided, CAD models were created to have a visual representations of the final design. As you can see here in the images, we have the final design for our solution, and it consists in the support for the sensors and the solar panels. The challenge, as said before, was to fit the magnetometer and its support inside the conical adapter. And it has two objectives. One is to support the magnetometers and these cameras, and the other one is to keep it as far as possible from the electronics to avoid interferences. To power these sensors, 4 panels were attached to the external surface of the conical adapter instead of using batteries in order to reduce the weight of the stage. The amount of these solar panels is meant to ensure exposure all the time.
Hello, I'm Carmen, and I will start talking about the logistic feasibility of this project. In terms of communication, we thought on adding an avionic bus for the building communication system of the rocket, which is intended to transmit and receive data from ground and use it also to transmit the sensor data. This transmitter is located in the avionic module with its antenna fitted in the external section of the avion stage. The transmission frequency is in the band of 2200 and 2290 megahertz, and the transmitted power is 10 watts. The additional payload, in this case the magnetometer and the camera, will have an additional power consumption. As we said before, for that, solar panels will be incorporated in the surface of the stage, together with an increment in the battery capability. To optimize the weight and the surface, it was decided to use panel intended for the 1U CubeSat. And here you can see a specification for a model from the HV technology, which cover really well our extra requirements, which is 800 milliwatts for the payload chosen.
Hey, I'm Amel. I'll be talking about the logistic feasibility. Continuing it. So I'll be talking about the logistic feasibility about the fuel mass. So after the primary mission, every vehicle should have enough fuel for station keeping and eventually the re-entry to Earth. So what we did was we used this basic fuel mass consumption equation, and we found the fuel consumed for every burn by the AVM. AVM has like 5 burns, there is 5 ignitions and 5 cutoffs. So we measured all that, and we found to have like 61 kilograms of fuel left. So with this amount of fuel left, we estimated an orbit transfer from 700 kilometers to 200 kilometers. Which is for our oral studies, and we did some vague estimations using rocket equations, and we found to have a certain amount of fuel left, and so we considered it as feasible, and we started with the GMAT simulations. We did the whole orbit transfer using GMAT and found the fuel left for the orbit transfer to be 25 kilograms. And yeah, this GMAT plot shows the orbit transfer, that you can see the top orbit and the decrease of 500 kilometer altitude, that is from 700 to 200 kilometers. And then we stayed there for like 2 days for enough auroral studies. And this shows the other window shows the desired altitude, semi-major axis. And yeah, that's it. Thank you.